Section 16.8 gives us some tools to understand why some acids are stronger than others, based on an understanding of the structure of the acid and its conjugate base. And so acid strength can essentially come from two factors. The hydrogen bond, and this isn't the intermolecular force hydrogen bond, this is the actual covalent bond between the acidic hydrogen and the rest of the acid. And what we're looking at is the strength of this bond. So weaker hydrogen bonds, perhaps unsurprisingly, are going to lead to an acid which will more readily give up its hydrogen. We can talk about the nature of that bond from a couple of different angles, which we will. And then two, the stability of the conjugate base. Okay, so this is kind of working from the other end. Acids and bases come in pairs, and the hydrogen bond we could summarize as like the stability of the acid. A less stable acid is more ready to give up its hydrogen. The stability of the conjugate base says that a more stable conjugate base is less likely to then reaccept that hydrogen backward, because acid-base chemistry is a dynamic equilibrium, and it's governed by the rate of the forward reaction as well as the reverse reaction. And so this is looking at it from the perspective of the base. And we'll go into particular details on both of these. So to start with, we'll look at figure 16.5. Remember, the pKa is the negative log of the Ka. And here we have some negative pKa values. Those are strong acids. Their Ka means that they're product favored in the ionization reaction with water. And remember, this is a logarithmic scale, so a pKa of negative 9.3 has a Ka on the order of 10 to the positive ninth. Anyway, so Hi is a very strong acid. That's why it belongs on our strong acid list. And HBr and HCl and HF are all similar to Hi, but you can see their pKa values show a widely different acid strength range. And if we look at the bond dissociation energies for these molecules, how strongly is the hydrogen bound to its halogen partner, we can see that a molecule like Hi has a weak bond. That's why it so readily gives up the hydrogen. If we look at HF, that's actually a pretty strong single bond. That's almost as strong as many double bonds. And so that's why the HF hydrofluoric acid is considered a weak acid with a pKa of 3.2. Now we can look at this from a different perspective and instead consider the bond length. And so iodine is a big atom. The iodide ion has a radius of 220 picometers. And so that means that the hydrogen is held far away from the iodine nucleus, has a longer bond length, and because of that, it's going to have a weaker hold on the hydrogen. And again, the hydrogen is more readily donated. That gives us this huge acid strength, a pKa of negative 9. And if we look down the line, HBr, HCl, and HF, this trend holds. The short HF bond length in hydrofluoric acid is what leads to the weak acidity of that compound. If we look beyond the halides, then we can consider the effect of electronegativity. So here we have pKa's of different compounds of a nonmetal bonded to hydrogen. Okay, so hydrofluoric acid right here, we've seen its pKa of 3.2. Water is actually, it's kind of a funny thought, but water is kind of like a similar molecule to hydrofluoric acid. It's just the nonmetal oxygen with some hydrogens attached. And its pKa is 14. Remember, that's like the value of Kw when water is acting as a acid. So water is a much weaker acid than hydrofluoric acid. And ammonia, NH3, we usually think of it acting as a base, but it can donate a hydrogen. It just has an extremely weak pKa of 38. And then methane is technically an acid as well. Its pKa is so small that it might as well not be an acid at all, pKa of 48. And so the more electronegative the atom that binds to hydrogen, the weaker the hydrogen bond and the stronger the acid is. Another way to think of this is that the more polar the hydrogen-fluorine bond is going to make that hydrogen more likely to be donated in an acid-base reaction. Right? The fluorine is so electronegative, it is stripping hydrogen of all of its electron density. The hydrogen is a bare proton exposed to the external environment without any electron density around it. And that's why it so readily makes new bonds through acid-base chemistry. And this same trend holds whether we're looking at the second row of the periodic table or the third or the fourth or the fifth. The more polar bonds are going to lead to stronger and stronger acids. Okay, let's turn the slideshow off there. Another way we can think about the effect of electron density is in nearby electron withdrawing groups. So if I have here I've drawn a structure for acetic acid, and the bond that we're interested in is this OH bond right here. And so that's a highly polar bond, and it has this COOH group, which hopefully you kind of recognize that that's a carboxylic acid group, formic acid, acetic acid, propionic acid. Those are examples of carboxylic acids that have this COOH group on the end. Anyway, we can compare just plain old acetic acid with chloroacetic acid. And this chlorine right here is a lot more electronegative than a hydrogen. And that means that electron density is kind of pulled toward the chlorine. And that's going to create a secondary effect of sort of pulling electron density from this carbon to the next, and from here, and finally it will actually affect this bond, which is 1, 2, 3, 4 bonds away. The presence of a single chlorine here is enough to make chloroacetic acid a stronger acid than regular acetic acid. And we can take this further. Right, and if we have trichloroacetic acid, then all three of these chlorines, they're like little electron vacuums. They're sucking up the electrons, and that is going to have an effect across the entire structure, weakening this oxygen-hydrogen bond and making trichloroacetic acid even stronger than chloroacetic acid and substantially stronger than regular acetic acid. And I don't have it here, but table 16.7 in your textbook gives you actual values for that. And so here we have a structural explanation for why this acid is stronger than that acid, because it's got these electron withdrawing groups which will weaken this oxygen-hydrogen bond and further expose that hydrogen so that it's ready to form new bonds through acid-base chemistry. Okay, now let's actually look at acetic acid, or let's just look at its simpler cousin, formic acid. So formic acid is a decently strong acid, and this is the bond that will be broken in acid-base chemistry. It's an oxygen-hydrogen bond, and we can compare that to something like methanol, which has a hydrogen-oxygen bond, but it is not acidic. So what is the difference between this hydrogen-oxygen bond and that hydrogen-oxygen bond? Well, true, we do have an electron withdrawing group right there, but that's not enough to account for the exceptionally large acid strength of carboxylic acids compared to alcohols that are similar in structure. So let's look at what the conjugate is to formic acid. We have HCOO minus, the formate ion. And this ion is actually one which exhibits resonance. So you're going to have to think back to 1220 for what resonance means and how to recognize it. But basically we could have done the double bond up to the top and the single bond to the right, or the double bond to the right and the single bond to the top, and those two structures are precisely exactly equivalent to each other as far as the bond strengths and geometries and things. And so in reality, the formate ion is going to sort of split the difference and share that double bond across both of those bonding centers. And resonance has the property of making ions particularly stable. It lowers the energy of the structure. And because the conjugate base of formic acid exhibits this resonance and is particularly stable, then that will drive the equilibrium to the right and make for a stronger acid than you otherwise might have guessed. And so all carboxylic acids will exhibit this. Formic acid, acetic acid, propionic acid, butanoic acid, all the others. And so the strength of carboxylic acids is explained by the resonance stability of the conjugate base, the anion that's left over afterward. And we can make similar arguments with all of our acids that have our oxyanions, H2SO4, H2SO3, HNO3, HNO2, HClO4, HClO3, HClO2. All of those are going to have anions which exhibit some degree of resonance. And what we'll find is actually the more resonant structures available, the stronger the acid. And so if we look at HClO4 versus HClO3 and HClO2 and HClO, well, these two are strong acids, and this one's a moderately strong acid, and HClO is a truly pathetic weak acid with a low Ka value. I forget what it is, but you know it's on the low end. And so the perchlorate ion will exhibit more resonance structures and a greater degree of resonance stabilization than the chlorite ion. A hypochlorite ion doesn't exhibit any resonance at all, and that's what makes it a pathetic acid, the hypochlorous acid. Okay, and so now you have an idea of how the structure, the bond strengths, bond lengths, the presence of electron withdrawing groups, and the influence of resonance is going to impact acid strength.